Hi, I'm Yasit Sandharwan. So we are in the third video of fan video series. In this video, we are going to discuss about fan performance curve. Okay, the fan curves. So the first curve we are going to discuss is the static pressure curve against airflow. So in the x-axis we use airflow, in the y-axis we use static pressure. So this will be the curve for static pressure development against the airflow. You can notice it is very clear when we increase the airflow, our static pressure is now decreasing. Let's see the reason for this. Okay. First of all, this point, let's say it is A, this point, middle point B, this point C. This A point will be shut off condition. We call this condition shut off condition. Zero airflow, maximum static pressure. And here maximum airflow but zero static pressure, we call that free delivery. Okay. So let's say draw a fan system here. This is the inlet, this is the fan, and this is the outlet. In shut-off condition, airflow is zero. Yeah, airflow is zero. That means airflow is completely blocked, like this. Although air is coming like this, they cannot pass through this block. Okay, so this is shut-off condition. Then we can go to point B. This is fan, this is the inlet here, this is the inlet, and this is the outlet. And this is the outlet. So in the B point, there is a certain airflow. So it is like this. So there is a space for air to pass through this hole. So that means there is a certain airflow. According to the point C, okay, according to the point C, there is the fan, then there is the inlet, and there is the outlet. Okay, so C, that means free delivery, maximum airflow. That means no any blockage. All the air output, which is the output of the fan, will be moved from this area. That means maximum airflow. So in this maximum airflow, what is actually static pressure? Static pressure means if we have a gas sample in a container, the pressure exerted on this wall can be identified as the static pressure. So in this case, the pressure on this wall is the static pressure. So let's assume that if you cover this wall, if you made this wall from some membrane of balloon, okay, so then there is the maximum airflow. That means there will be no any pressure on the balloon membrane, okay, on this balloon membrane. But what if you block this airflow to a certain amount, then what will happen is there should be some pressure exerted on this balloon membrane, and you can notice if it is made from balloon membrane, this will form like this. Due to the static pressure development, balloon membrane will form like this. if we block the air. In the third, that means the condition A, if you completely block the airflow, and if you make this outlet with balloon membrane, you cannot make duct with balloon membrane, but just assume it may look like this. Okay. So, if you block your airflow like this, that means airflow is reduced. Airflow is reduced. If you block small stream of air will come out, that means decreased airflow. So if you block the airflow, that means airflow is decreased. Here you don't get much air if you block it. So if you block the airflow, airflow will be reduced. That means if you reducing the airflow, what happens is static pressure development inside will be higher. That is why when we go down from this direction, in this direction, that means airflow is reducing. That is why static pressure is increasing. At the maximum point, we have the maximum static pressure when we do not have any airflow. That means zero airflow, maximum static pressure. But here in this free delivery, you have the maximum airflow. Because of that, no pressure will be exerted on this balloon membrane. That is zero static pressure. But the thing is, theoretically, you cannot practically achieve these 2 points. These 2 points practically we cannot achieve. But the thing is, this is how static pressure will change against the airflow. That is the reason. Okay. Then another thing you have to be aware is total pressure. Total pressure. In this graph, I have drawn the static pressure, but you know about static pressure, it has two components, static pressure and dynamic pressure. Dynamic pressure is due to the velocity. If we increase the airflow, velocity will be higher. That means dynamic pressure or the velocity pressure will be like this. Velocity pressure will be like this. So this is the dynamic pressure or the velocity pressure. Dynamic pressure, and this will be my static pressure. Total pressure is the summation of those two. So if I draw the total pressure, it may look like this. So this is the total pressure. Okay. In this point, your static pressure is 0. You have a certain amount for dynamic pressure. So for the total pressure, if static pressure is 0, you have certain amount for dynamic pressure, let's say x, then the total pressure is also x. That is why it is came to this point. In this point, dynamic pressure is 0, but you have certain amount for the static pressure, let's say it is y. So what is the total pressure? Y. That is why it's begin with this point. Okay. Then you can imagine the middle points. So that is how total pressure differ with the airflow. Okay. Then other thing now is, so this is actually static pressure. What happens if we change the speed of the fan, let's say we decrease the speed of the fan, what happens? Static pressure development will be decreased by small speed. They cannot deliver much static pressure, and also airflow is now decreased. Because of that, you are decreased. Due to decreased speed, your fan curve may look like this. So if you increase the speed, static pressure and the airflow will be higher. Your fan curve may look like this. Okay. So this is the highest speed, second highest, and the lowest speed is this curve. So keep in mind, if your speed of the fan is decreased, fan curve should be move in this direction. Okay. Then actually up to now we discussed about this static pressure against the airflow. Okay. So this static pressure can be categorized into two types. First one, positive static pressure. The second one, negative static pressure. Actually, positive static pressure is the static pressure we have drawn now. There is another word for positive static pressure. It is available. That is available static pressure. That means, let's say you have a fan system. This is the inlet. This is the outlet. This is a damper, and there is a place where diameter is reduced and diameter is increased. So this is our fan system. You want air to move from this system. To move from this system, your air sample, your air stream should have some potential, should have some energy to move from here to here, because there can be pressure losses due to these bands, due to these dampers. In here diameter is reduced. When the air is moving through this system, there can be pressure losses. To overcome this pressure, your fan should have some energy. Okay, so if you want your fan to deliver air from this system, from this place to this place, your fan should have some energy. That energy is the energy this system requires from the fan. This system requires that much of energy to move your air from here to here. That required energy is the negative static pressure. Positive static pressure or the available static pressure is the pressure which this fan can deliver. One thing, that is positive static pressure, is the static pressure this fan can develop. Negative static pressure is the pressure which this system requires. Okay. As an example, this system, if this system can talk, they will say, if you want to move the air from here to here, you have to have this much of energy. That is negative static. If the fan can talk, he will say, although you need this much of energy, I can only produce this much of energy. That is available static pressure. So that is this is the curve I have drawn, we have discussed. So let's see about negative static pressure or the required static pressure. There is another name for that. We call that system resistance. Okay, system resistance. Let's draw that curve. Okay. Airflow. Here the system resistance curve should be like this. That means if we increase the airflow, system resistance is also increasing. What is the reason for this? As an example, let's see, if you have 3 students to move from one small door, they will move, but let's assume there are 30 students to move from same door. In which situation we have higher resistance? When we have 30 students. So likewise, if we have more air particles, system resistance will be higher. In another way to look it, let's say if airflow is higher, what happens is the momentum is also high. What is momentum? Speed multiplied by mass. Okay. If you want a quick general idea of the momentum, let's say if you are hit by a foot cycle and compare it to if you are hit by a huge lorry, in which situation you have the higher damage if you hit by a lorry, because the momentum is higher. Momentum is the product of speed and the mass. So airflow is increased mean this is increased. Speed and the mass is increased. That means momentum is increased. If the momentum is increased, when the air particles move from these type of system, energy loss will be also higher. So there is a higher momentum in this air, and if they hit those obstructors, the energy loss will be higher. Actually, if the resistance is higher, energy loss will be higher. So we can conclude that there is a higher energy loss. That means system resistance is higher. Why? When system resistance is higher, when energy loss is higher, let's say you are going to start new thing, something new, and if some of your friends put some negative thoughts on you, that means a resistance on you, your potential may go down. So it is like this: if the resistance is increased, your potential energy loss is increased. Okay, so airflow is increased mean momentum is increased. If the momentum is increased, if they hit those obstructions, energy loss will be higher. That means resistance is high. That is why if we increase the airflow, system resistance is high. Okay, that means if you increase the airflow, energy loss will be higher. That means system resistance is high. So up to now I have explained what is the reason for this curve, the shape of this curve, the reason for the shape of this curve in same system. So don't let's say same system, how system resistance will change if we increase or decrease the airflow. In the second example, I will tell you the reason. What happens if the system changes? Previously I have explained you in same system what happens if you change the airflow to the system resistance. Now I am telling you what will happen if you have changed the system. let's say in this system I have a damper which is 25% open, and in this system I have a damper which is 50% open, and I have a damper in this system 75% open. All the other things are same except for damper open. Then this system have a separate system curve, that is this system curve, system resistance curve. This system should have a separate one, and this system should have a separate one. If I draw these system curves, they should be like this. Let's say this is A, this is B, this is C. So how you can decide which is A, which is B, and which is C? So if you notice, if it is 25% open means 75% closed. That means 75% they have blocked 75%. The air is blocked. Okay, air is blocked by 75%. That means resistance is higher here, so much higher. In this exam, in this situation, 50% is now open. Air can move more than this situation. That means system resistance is high but not than this. In here, 75% open means 25% blockage is there. So air is blocked by only 25%. That means resistance is now very low. Okay, here very low, here very high. If you have open only 25%, okay, only 25%, airflow is not much. Airflow is now reduced. Only 25% is open. So not very higher amount of air can move through the damper. But here, if you have open 75%, that means a large amount of air can move from this damper. That means airflow is increased. So you can clearly see when the resistance is decreased, airflow should be increased. So this should be A, this should be B, this should be C. That is 25% open, 50% open, 75% open. If you can notice, if the system resistance is reduced, that means 75% open, that means only 25% is closed. That means very little resistance. Very little resistance means airflow is now high. Likewise, if you increase the resistance, your fan curve should move from this direction to this direction. That means more airflow. Here, low airflow to higher airflow. 0 to maximum. So that is why your system resistance curve should move from here to here when the resistance is decreasing. When resistance is decreasing, your system resistance curve should move from here to here. So as a summary, system resistance, when system resistance is decreasing, your fan curve should, your system resistance curve should move from in this direction. Previously I told you, if fan speed is decreasing, your static pressure curve should move from top to bottom. Okay, so you can keep this thing in your mind. Okay, then we can combine those two fan curves. Let's see. This is static pressure. Okay. This is airflow. Okay, and this is static pressure. If you draw the system resistance curve in this curve, so this will be the system resistance curve. Let's say okay, and let's we draw the fan system. So this is the fan system. This is our fan. This is inlet. This is outlet. Okay. So for this fan, this is the system. Sorry, fan curve. For this system, this is the system curve. If someone want this much of airflow, okay, this much of airflow, that means according to the fan curve, what is the pressure the fan can deliver is this. In other words, what is the available pressure according to this fan is this pressure, is P1. But according to the system, according to this duct system, what is the pressure they require is this much. Okay, if you want this much of airflow from this system, fan can only deliver this much of static pressure, but in order to move air from this to this area, the system require this much of static pressure. So this thing doesn't work because you need this much of static pressure, but only fan can deliver this much of static pressure. But if you decrease this airflow gradually, these 2 points here, these 2 points will meet here. Okay, ultimately this will meet here, and we can call that and the operating point. So according to this point, okay, this is the airflow they want according to the fan curve. So static pressure curve, what is the pressure they can deliver? This is the pressure. Okay, but according to the system resistance curve also, this is the airflow they want, and this is the system resistance or required static pressure they want. And also according to the fan static pressure, they can deliver that pressure. So according to this system curve, this is the pressure they want, and according to this curve, this is the pressure they can produce. Now their requirements are satisfied. They require 100 pressure, and the fan can give 100 pressure, like this. So that is called the operating point of the fan. Actually, if we switch on the fan of this system, this system works in this point. That means we can obtain this much of airflow, and fan can give this much of static pressure. So actually the fan is now working according to this operating point. Okay, so that is called the operating point. When it comes to the operating point, normally it is recommended to have the operating point in the right side of the curve, but not in the left side of the curve. If you have a curve like this, and let's say your operating system resistance is like this, that means your operating point is here, which is on the left side of the curve. That is not recommended. That is not recommended. Okay, on the left side of the curve is not recommended to have a operating point. So your operating point should move to the right side. How do you do that? Let's see. There are options to do that. This is the airflow, static pressure, this is the system resistance. Okay, so if you decrease the system resistance, how do you do that? One option, you can, let's say originally your damper is 25% open. You can increase it to 35%. Now system resistance is decreased. Originally you are blocking 35%. Now it is, you are blocking only 65%. That means system resistance is decreased. More air can move from the damper if you change from this condition to this condition. So your system, if the system resistance is decreasing, I told you, your system resistance curve move from this direction to this direction. That means new system resistance may look like this. So you can clearly see your original fan curve operating point was here. Now it was here. It is here. Originally airflow is like in this point, and operating point, static pressure in this point. But according to the new static operating point, your airflow is increased and your static pressure is decreased. Okay, so that is one way you can move your operating point along this curve. Then what happens if you increase the system resistance? Your curve may move in this direction, from this to this curve, if you increase the system resistance. And also your system operating point will move, but to the left side. However, you can move your operating point like this. Another way to move your operating point is increasing or decreasing the fan speed. So you now know, if you decrease the fan speed, your fan curve may move from top to bottom like this. Original fan curve was this, and if you decrease the fan speed, curve may move from this to this. Now your operating point is here. Assume that you haven't changed your system resistance. Okay, so this is the system resistance. This is the new fan static pressure due to decreased speed. So this will be your new operating point. So according to that, your original airflow was there and your new airflow was there. Here your static pressure original static pressure was there, and your now new static pressure was there. Okay. That is how another thing. Sorry, if you increase the speed, your fan curve may look like this. Okay, then this will be the new operating point. According to that, this will be the new airflow, and this will be the new static pressure. Okay, so that is how you can move your operating point here to here. Okay, so there are options: increase or decrease speed, change your fan system to increase or decrease your fan system resistance. Okay, so if you analyze what are the best options to decrease the speed or increase the speed. If you increase the speed, you can clearly see static pressure is increased. If you decrease the speed, static pressure is decreased. What are the best options? We can talk those things, or we can analyze those things in upcoming video. In this video, I just wanted to tell you that is how we can change the operating point. Okay, so at the beginning I told you it is not recommended to have an operating point on the left side of the curve. Then I will tell you the reason for this. Okay, first reason. Actually, airflow, static pressure. Actually, this fan curve is a generalized form. For any fan, we can generally draw that fan curve like this. But if you specifically draw the fan curve for radial blade, forward curve and backward curve fans, it may look like this. Okay, so this fan curve will be our forward curve, this fan curve will be our radial fan curve, this fan curve will be our backward curve fan curve. Okay, especially if you note the forward curve fan, okay, it may look like this. We call that region, there's a dip in this region, we call that region stall region, which is not good. Okay, I will do a separate video for this stall region, why it is occur, what is stall, how to get rid of this thing, like those kind of things I will cover in that video. But here I just wanted to tell you, keep in your mind that when your operating point in the stall region, let's say your system resistance curve is like this, that means your operating point here, that means your operating point is inside the stall region, which is not very good. In this region, fan does not perform in very stable conditions. Okay, so it is not good to have your operating point in this area, in this stall region. Okay, stalling is occurred, or stalling happens when the airflow is decreased. Okay, when the airflow is decreased. In the fan curve, which side we have the decreased airflow? So this is the airflow axis. Airflow is 0. Airflow is maximum. So airflow is decreased in this area. To the left side of the curve, we have decreased airflows. So that is why in left side of the curve, we got stall region. and it is not very stable condition to a fan to operate. Okay, because of that we do not recommend the left side of the fan curve. So that is one reason. Other reason is this is fan curve, static pressure curve, this is airflow, and this will be system resistance curve. And if you draw the static pressure, we discussed those things in detail in the previous video. Go, if you haven't watched this video, go and watch the previous video. We in detail explain the static efficiency, total efficiency, those curves, those things in the previous video. So in this video I would draw the static efficiency. Okay, static efficiency is equal to static pressure rise and multiply airflow cubic feet per minute and input power. Okay. In this situation, airflow is 0. That means this is 0. Okay. That means total efficiency is also 0. So total efficiency should be begin in this point. And when it comes to maximum airflow, that means this position, static pressure is 0. Although this airflow is at its maximum, static pressure goes to 0. Now you know the reason for that. Static pressure is 0. Why? You know the reason. So, however, this is 0. Because of that, static efficiency is also 0. So, in this point also, static efficiency should be 0. So, efficiency should change like this. Okay. So, this green color dash line represents the efficiency curve of this fan. Okay, so the highest point is the best efficiency point. Okay, highest efficiency point, we call that best efficiency point. If I draw a line through the best efficiency point, okay, and if you can take your system resistance curve to this area, your operating point exactly will be on this point. That means if you measure the efficiency at its maximum. So it is very good to have your operating point in this position. But the thing is, practically we cannot take the operating point exactly on this position. Because of that, they recommend this small region around the best efficiency point. That means this range, so they recommend at least your operating point should lie on this region. That means in this region. So your operating point should lie on at least on this region. Definitely this range does not lie on the left side of the curve. Okay, that is the second reason why we don't recommend the left side of the fan curve to operate your fan. Okay, So that is those are the reason we do not recommend the left side of the fan curve. Okay. Then as today video is about fan curves, I would describe last type of fan curve, that is BHP curves. I have already covered that part in previous video. BHP curve against airflow, that is brake horsepower. For the backward curve fan, it may look like this. For the forward curve fan, it may look like this. For the radial, it may look like this. Okay. So this is backward curve, this is radial, and this is forward curve. So if you can notice, brake horsepower means how much of energy we should give to the fan in order to rotate. That means to the motor, how much of energy we should supply, that input power, brake horsepower. So you can notice that for the backward curve fan, if we increased airflow, the power will increase to a certain amount, then it won't increase anymore. It will be constant or slightly decreased. We call that it is good. So if you increase the airflow, it is good because it doesn't require a higher power, which is very good. We call that non-overloading characteristic. So if you match your motor to perform even in this position, that means the highest power, if you match your motor to perform even in this position, your motor does not overload in any condition you perform by this fan. Because if you increase the airflow, what happens? Your power requirement does not go higher. But the thing is, let's say if you select a fan with this airflow to the forward curve fan. Okay, but let's say your airflow is now increased to this amount. Okay, let's say to this amount, very small amount. What happened is your power requirement as goes up. Yes. So there's a possibility your motor can overload because higher power requirement. Your power requirement is increased a lot due to this change in airflow according to the forward curve fan. But according to the backward curve fan, it does not happen. So this is non-overloading, and we call that overloading characteristic for the forward curve fan. Forward curve fan. So this is brake horsepower curves for the fans. So in this video, I just wanted to discuss those fan curves. Okay. So in the next videos, we are going to talk about fan loss, fan stalling, fan selections, those things. So let's meet in the next video.